Okay, so what we'd like to do now is get some intuition into what beta and gamma are. We know how to calculate them. Now we want to know what do they mean. So to do this, let's study the simplest possible case that we can consider. And if you look at the Cullen-Samanzik equation, the simplest case would just be, let's study G2 of P. So I'm going to start off just doing a few manipulations, just so that when I write down the solution to the Cullen-Samanzik equation, you'll be able to verify it. Okay, so we're working in D is equal to 4 dimensions. Something that we've done a few times, we've worked out what are the dimensions of the field. And I'll just write down the physical field. The dimensions of the physical field is inverse of length. I'm sure that you can all get that. I'm not going to redo it. If we then study the 2-point function, actually, let's be a little bit explicit. So let's say the vacuum expectation value of the time ordered 2-point function, phi p of x1, phi p of x2. So this is a specific correlation function that we might study. And then the Cullen-Samanzik equation is an equation for the Fourier transform of this. We always like to study the Fourier transform of the correlators. And then we will have G2 of P. So if we look at this equation and we start to assign dimensions, well, on the left-hand side, we've got Bra vacuum and Ket vacuum. They are dimensionless because we know the vacuum is normalized to 1. So the only thing that has dimension is the physical field. So this side of the equation is length to the -2, 1 inverse length for each phi. And then in the units that we are working, where h bar is equal to c is equal to 1, we know that momentum is length to the -1. So this d4p is going to be length to the -4. The exponential, of course, is dimensionless because momentum is length to the -1 and x is length, so that's dimensionless. So to get dimensions to match, we know that G2 of P has to be length squared. Okay, this is just dimensional analysis, but what we have concluded is that G2 of P has to have dimension of length squared. This means it scales like an area. If we change our units so that momentum were to double, we would expect G2 of P to decrease by 1/4. Okay, good. Okay, so let's now, this is just by dimensional analysis, let's write down a formula that has to be true for G2. So here's G2 of P. I'm going to pull out a 1/P squared. All that does, it makes sure that I've got the dimensions correct. And then this could be multiplied by any function of P over M. You see, that's dimensionless. I can depend on P over M in any way I like. And the physical coupling, G physical, which is also dimensionless. So this equation that I've just written down over here, the only content in this equation is dimensional analysis. Okay, so you should be able to derive that yourself. Now, because I have written down a function that depends explicitly on M and P, and I've been clear about how the P and M dependences, I can actually rewrite the Cullen-Samanzik equation, and I'm going to trade my d by dm derivative sitting over here for d by dp derivatives. I'm going to write down the result. This is a great thing for you to verify. It's a little exercise. I am certain that you can do it. The result of this exercise is that the Cullen-Samanzik equation becomes P d by dp plus 2 minus beta d by dgp minus 2 gamma onto G2 is equal to 0. Good. Okay, so as I said, this is all just dimensional analysis. Now, all I want to write down is I want to write down a solution to this last equation. So the solution is the following. G2 of P will be equal to, we'll have 1 over m squared. We will have curly G of G bar. I'm going to have to tell you what G bar is. Curly G is some arbitrary function of G bar. So by saying that this solves the Kalan-Samanzik equation doesn't tell you what curly G is. And then we've got e to the minus, we've got an integral. The integration variable is d log p primed over m. And we integrate from p primed is equal to m up to p primed is equal to p. And what are we integrating? We're integrating 2 minus 2 gamma. And in general, our anomalous dimension gamma will depend on p. So this is going to be a complicated integral to do. Now, let me tell you what G bar is. G bar satisfies this equation, dg bar d log p over m is equal to beta, the beta function, as a function of G bar. Okay, so we can see the two functions appearing in the Kalan-Samanzik equation appear in our solution. And when we solve this differential equation for G bar, we have to make sure that G bar at P is equal to M is actually the physical coupling. Good. So the important thing that we've written down so far is this solution in the red box. This is the solution to the Kalan-Samanzik equation. And by thinking about this, we are going to learn something about gamma and beta. So the important stuff comes now. What we did up to now was just so that I've given you enough background that you could check the solution if you like. The important stuff is coming now. We want to interpret things. So let's do the following. Let's again make the problem simpler. That's whenever you want to understand some physics, you make the problem as simple as possible. So now I'm going to make the problem simple. I'm going to imagine that gamma is a constant. In general, it won't be, but I'm saying, let's just imagine that gamma is a constant. Then what will our G2 of P look like? So our G2 of P will be equal to, well, we'll have the 1 over m squared. Okay, no problem. We'll have our curly G of G bar, fine. Then we'll have e to the minus. Now, this is a constant. So we can pull the 2 to the 1 minus gamma out of the integral. And when we integrate d log p prime over m, we're just going to get the log of p primed over m. So that's a trivial thing to evaluate. That's a trivial integral to do. And then we need to evaluate this between the two limits. When we plug in p primed is equal to p, we'll get log p over m. And when we plug in p primed is equal to m, we'll get the log of m divided by m, which vanishes. So we'll only get a contribution from the upper limit, and it'll be the log of p over m. Good. So that's what we get doing the integral in the exponent. And we were able to do the integral in the exponent because now gamma is a constant. So that's how we simplified the problem. Okay. So now, of course, we've got e to the minus 2, 1 minus gamma to the log p over m. Well, we can take this 2, 1 minus gamma and raise p over m to that power. And then e to the log of anything is that thing. So what do we get? Plug it in, just use rules of logs. I'm not doing anything sophisticated at all. And what you get is e to the minus 2 gamma. The 1 over m squared has cancelled. And then we've got p to the 2 minus 2 gamma. And we've still got curly G of G bar. Okay. So this is what G2 of P looks like. So let's try to interpret this a little bit. It's a rather interesting result. Okay. So this is m to the minus 2 gamma over p to the 2 minus 2 gamma g of g bar. Right? Let's just correct that. G bar. Good. Now notice something. Before, just by dimensional analysis, we knew that the 2-point function behaved like length squared, like an area. So we expected g2 of p to be like 1 over p squared. So if g2 of p is length squared, it means you expect g2 of p to be like 1 over p squared. So if you double p, g2 of 2 times p, what would this give you? Well, this would give you 1 over 4 g2 of p. This is what you expect, okay? This is like a scaling law that you would get from dimensional analysis, and you would say it's because this thing has dimension 2. It's 1 over 2 squared. This is what you expect. What do we actually get? That's what you expect. Actually, what we get is g2 of 2p, take a look at our formula over here, is 1 over 2 to the 2 minus 2 gamma. So you can see that the dimension of this thing, this 2 from the length squared, okay, so let's just, this 2, which is the dimension of this thing, is that 2, that's been changed into 2 minus 2 gamma. And that's why gamma is called an anomalous dimension. And where did this anomalous dimension come from? Well, you should remember that gamma, how did we get gamma? Gamma was something like 1 over m d log z dm. So it came from the wave function of normalization. When you change the momentum by changing units, of course you've changed the field strength because the field strength has a unit, but you also have to keep rescaling the field so that it keeps producing a particle with probability equal to 1. And that extra rescaling is what the wave function in normalization does, and that lands up causing the Green's function to scale in an anomalous way. It no longer scales as if it has a dimension of 2, it scales as if it has a dimension of 2 minus 2 gamma. So that's why gamma is called the anomalous dimension. Good. Now, let's focus on beta. What is the meaning of beta? So, what is the meaning of beta? Again, let's try to simplify the problem. So to simplify the problem, let's set, let P equal to M. So now if we let P equal to M, then we know that G bar at P is equal to M is the physical coupling. So when we look at our solution for G2, so where is it? Over here. G2 of P will be equal to 1 over M squared times by now this will become G of GP. So G2 of M, G2 of P, sorry, will now be 1 over M squared. And then we will have this function now as a function of the physical coupling. And then when we look at this exponential that we've got here, well, we integrate from p prime is equal to m up to p prime is equal to p. So if we put p is equal to m, the exponential doesn't contribute at all. And what we land up getting, this is the answer for the Green's function. G2 of p is just 1 over m squared g of gp. We could expand this. Expand. And what will we get? We'll get a series expansion in GP. Series expansion in GP. But you know what it means if you get a series expansion in GP. this is the perturbation series. So in actual fact, this curly G of GP, this is nothing but the perturbation series that you would get by summing the Feynman diagrams. We will continue in a moment.